Welcome to 50 Facts Explained, the channel where curiosity meets clarity.
With this video, we will leave 50 amazing facts about fusion energy, the artificial sun. Fusion is the process that powers stars. Scientists are trying to build it on Earth, and Fact 50 will show you why. If it works at scale, it could rewrite civilization. One star power fusion is what powers the sun. Hydrogen atoms combine into helium. A tiny bit of mass becomes enormous energy. To Einstein's equation, net energy comes from E equals mc. A small loss of mass converts into pure energy. It's physics at its most extreme. Three opposite of fission fusion joins atoms together. Fission splits them apart. Same nuclear family, opposite direction. 4 no carbon emissions. Fusion doesn't burn fossil fuels. No carbon dioxide during operation. Clean energy at the reaction level. 5 fuel from water fusion fuel can come from deuterium in seawater. Oceans contain vast supplies. Energy potential is enormous. 6 extreme heat fusion requires temperatures over 100 million degrees Celsius, hotter than the sun's core. Heat is the barrier. 7 plasma state. At those temperatures, matter becomes plasma. Electrons separate from nuclei. It's a charged, glowing soup. 8 magnetic bottles. Scientists use magnetic fields to contain plasma. Physical walls would melt instantly. Magnets act like invisible cages. 9 tokamak design. A tokamak is a donut-shaped fusion reactor. It uses powerful magnets to confine plasma. The shape stabilizes the swirl. 10 stellarators twist the magnetic field into complex loops. They aim for more stable confinement. Engineering meets art. Now the challenge becomes clear. 11 Coulomb barrier atomic nuclei repel each other electrically. Overcoming that repulsion takes extreme pressure or heat. Fusion fights electrostatic force. 12 net energy problem. For decades, reactors consumed more energy than they produced. Ignition remained out of reach. That was the central obstacle. 13 ignition milestone. In 2022, scientists achieved net energy gain in a controlled fusion experiment. More energy out than laser energy in. A historic step. 14 laser fusion. Some reactors use giant lasers to compress fuel pellets. Light squeezes matter inward. Pressure triggers fusion briefly. 15 magnetic versus inertial. There are 2 main approaches, magnetic confinement and inertial confinement. Continuous control versus rapid burst. Different paths to the same star. 16 no chain reaction fusion doesn't run away like fission can. If conditions fail, the reaction stops. Safety is built into physics. 17 minimal long-term waste fusion produces far less long-lived radioactive waste. Materials can still activate, but decay times are shorter. Cleanup is simpler. 18 helium byproduct fusion of hydrogen creates helium, the same gas in balloons. Harmless compared to nuclear waste rods. 19 tritium challenge. Some fusion reactions use tritium, a rare hydrogen isotope. It must be bred inside the reactor. Fuel logistics matter. 20 breeding blankets reactors can use lithium blankets to generate tritium. Neutrons hit lithium, creating new fuel. The machine feeds itself. Right here, scale becomes the issue. 21 ITER project. The ITER project in France is the world's largest fusion experiment. Dozens of countries collaborate. It's global science. 22 superconducting magnets. Fusion reactors use superconducting magnets cooled near absolute zero. Extreme cold contains extreme heat. Opposites cooperate. 23 plasma instabilities. Plasma is unstable and turbulent. Tiny disruptions can shut reactions down. Control is constant battle. 24 magnetic reconnection. Sudden magnetic shifts release energy inside plasma. It happens in the sun too. Earth reactors mimic cosmic physics. 25 energy density fusion fuel contains millions of times more energy per kilogram than coal. A small amount powers cities. Density changes logistics. 26. No meltdown risk fusion can't melt down like fission plants. Without sustained conditions, it stops. Failure equals shutdown. not explosion. 27. Neutron damage. High-energy neutrons bombard reactor walls. Materials degrade over time. Engineering durability is critical. 28. Advanced materials. Researchers develop special alloys and ceramics. They must survive heat and radiation. Materials science is as important as physics. 29 times scale commercial fusion is not tomorrow. It's decades of engineering away. Progress is steady, not instant. 30. Private investment. Private companies now invest billions in fusion startups. Innovation speeds up. Competition drives breakthroughs. Stay with this because impact reshapes geopolitics. 31. Energy independence. Fusion fuel is globally available. No single region controls oceans. Power dynamics could shift. 32. Base load power. Fusion could provide constant electricity. Unlike solar or wind, it doesn't depend on weather. Stability matters. 33. Grid transformation. Abundant energy would reshape power grids. Storage challenges shrink. Infrastructure could simplify. 34. Desalination potential. Cheap fusion energy could power large-scale desalination. Fresh water becomes easier to produce. Water scarcity shifts. 35. Hydrogen economy. Fusion could produce green hydrogen cheaply. Clean fuel for industry and transport. Energy ecosystems expand. 36. Space applications. Compact fusion reactors could power spacecraft. Long missions become feasible. Interplanetary travel changes. 37. Artificial suns. Fusion reactors replicate stellar processes on Earth. Humanity builds miniature stars. That's engineering at cosmic scale. 38. Scientific spin-offs. Fusion research advances superconductors, lasers, and plasma physics. Technology spills into other industries. Even partial success pays off. 39. Energy equity. If fusion becomes affordable globally, energy poverty could shrink. Development barriers fall. Opportunity spreads. 40. Climate impact. Fusion alone won't solve climate change instantly, but it could provide massive clean energy. Scale changes outcomes. Now we reach the deeper implications. 41. Contained star. Inside a fusion reactor, plasma is hotter than the sun's core. Yet it's held by magnets. Human control contains stellar force. 42. Decades of persistence. Fusion research began in the 1950s. Progress has been slow but cumulative. Patience builds revolutions. 43. Lawson Criterion. Scientists use the Lawson Criterion to measure fusion conditions: temperature, density, confinement time. All three must align. 44. Ignition versus commercialization. Achieving ignition is not building a power plant. Scaling engineering is harder. Science proves possible. Engineering proves practical. 45. Magnetic fields stronger than Earth's fusion magnets can generate fields tens of thousands of times stronger than Earth's. Invisible strength shapes plasma. Force without touch. 46. Energy return ratio. The goal isn't just net gain. It's high gain, much more energy out than in. Economics define success. 47. No fuel transport trains. Fusion fuel quantities are tiny compared to coal shipments. Logistics shrink dramatically. Energy density reduces infrastructure strain. 48. Global collaboration. Fusion research crosses political borders. Shared knowledge accelerates progress. Science becomes diplomacy. 49. Civilizational leap. If fusion becomes scalable, energy limits loosen. Manufacturing, transport, computing all expand. Abundance rewrites constraints. 50. Harnessing the sun. Fusion is humanity attempting to control the force that lights the stars. If mastered, we won't just generate electricity. We will replicate the core process of the universe itself, safely, on demand. And that could mark the moment we stop merely using energy and started shaping our destiny with it. And that wraps up of our journey through 50 facts explained about fusion energy, artificial sun. If you enjoyed this, subscribe for more facts that actually matter.